Hello, wonderful world of the internet. My name is Caleb from CTVM2. This video we will be discussing binary, and I'm going to go pretty in depth. So, for those of you who don't know, I have made other binary videos in the past. I have probably like 4 or 5 over all kinds of different things, and they got a lot of views. I mean, one of them's I think almost 30,000, which is pretty awesome. But anyways, this video is going to be a little bit more laid back, a little more chill. I might do some other things like answer some questions or from comments and whatever else. So I'm having some difficulties. Right now I'm using a normal camera, and I'd like to use this camera, Logitech C920, because the video quality is fine, and I have a pretty awesome microphone over here, which is out of frame, but it's pretty awesome. But I'm having this most ridiculous problems ever. I don't know. So whatever. I'll figure it out someday, maybe. I don't know. But that'd be a lot easier because then I can just record it directly on my computer, and I can use that better microphone without having to make it super complicated. But anyways, let's begin, I guess. Alright, so first things first, this video was supported by Patreon. So for those of you who don't know, I have an account on Patreon, and there you can support me on a video by video basis. So what that means is that I make a new video and you pay me X dollars or pennies or whatever. Now that being said, I do make a lot of videos. It's not like I make a video once a month, so generally I'd expect the video payment to be rather lower compared to the other people on Patreon. So if you give me a second here, I will either give you the name of the person who I'll feature in this video, or I will either just put it on there in text if I can't pronounce it. So, Patreon is cool because if I get enough followers, I'll have a continual income. So if you guys want to help me with that, that'd be really awesome. And that'd be good because then I would know that you guys support what I'm doing and also that you want to see more videos. I'd rather you pay a little bit for a long period of time because you actually can put a maximum on there. So, I'd rather you just put the, let's say, I don't know, 20 cents per video. That's cheap, because then that's like, I don't know, a couple bucks every month, if that. So that's cheap for you. I'd rather you do that than pay me a couple dollars per video for 10 videos or whatever, because then down the road I'm gonna run out of that income, which won't be good. I'd rather continually have that source of income. So the supporter for this video is Sunshine. So thank you, Sunshine. Thank you for the support, and thank you for brightening everybody's day. I mean, without Sunshine, it'd be pretty dull, you know. All right. So if you want to be featured, I don't even know I have a machete. But anyways, if you want to be featured in video, go support me on Patreon. Thank you. Alright, so to begin, first thing, I want to give an introduction to binary. So, what binary is how computers communicate. You've probably heard that before. All computers work in binary, but what does that really mean? Well, it's a concept thing. It's a complex concept, so it can take some time to really understand. And it's just important to understand that binary can be used in different ways depending upon your application or what you're doing it in. So, for example, you can do binary in a normal math class, not having anything to do with computers, and it can still make sense. This binary is referring to binary of actual computing, so electronics, that kind of binary. So, binary is a way to represent ons and offs, because when we're talking about digital electronics, Everything is either on or off. That's how the core of electronics works. At the smallest fundamental level, the movement of electrons, you're either on, meaning there is an electron flow, or you're off, there is not an electron flow. That's represented with the numbers 1 and 0. From there, understand that it gets more complex, meaning you can have larger numbers, like for example, we could have 101. That could represent something, either a larger number, or you can use that to represent a sound, or part of a picture, or part of something, anything else. So basically, the way the binary is used on the application level differs. Binary can be used to create audio, but it can also be used to create video. And the way that works is how the encoding is. For example, the ASCII, some people say ASCII, but I don't know. That's a way of encoding letters and numbers using binary. So the string of 01101 or whatever would be interpreted as a specific number or letter. That's a little different than using binary in a math class where 101 represents a specific number and that's all it represents, just the number. So to begin with, we're going to start with just looking at binary from a mathematical standpoint and applying that to computing. So what I mean by that is that when you understand how the binary counting system works, the numbering system works, then you can start to understand what it means to have an 8-bit number or a 64-bit operating system, or what it means to have a bit depth on audio of 32, and so forth. But it just takes some time to kind of get used to it. So the thing to understand with binary is that it's digital, it's a representation of something that is real. So before we had binary, we had analog electronics. And what that was, it was like the actual creation of whatever it was. So if you had analog audio, it was the actual audio. And if, let's say, you put that on a timeline and you zoomed in indefinitely, it would continue to be smooth and flowy, right? But if you're using binary to recreate that audio as close to possible as the original, well then if you zoom in and you keep zooming in, you're going to start seeing bars, because everything is represented as either on or off. So, you know, you got little, it's not a continual flow, whereas analog, it basically, in theory, you could zoom in and basically look at a second, and then a millisecond, and then a microsecond, and then a microsecond of a microsecond. I don't know what that's called. And it would still look flowy because it's the actual audio file. Or it wouldn't even be a file. In that case, it'd be the actual audio. That being said, the rate at which you have the changes, basically to recreate the audio as close as possible in binary, that's called the sampling rate in audio. So, like standard CDs are 44.1 kilohertz. Or, yeah, I think that's right. Yeah, so what that means is every hertz is basically one individual sound or binary representation of a sound, and they do that 44,100 times per second to recreate audio as close as possible. Personally, I like to see audio as I like to use audio as an example to explain binary, because I just think it's clear on how you're not actually having the actual audio, you're recreating it using binary representations of the audio. And then when you play it back, the audio is read and played back as sound, which is basically how the audio is created. You're capable of understanding that binary because the binary presents itself in a way that makes sense to us audio. So it's complicated, so let's just start from the basics of number system. This is how you count in binary, basically. So let's begin. You are my sunshine, my only sunshine. You make me happy. Oh, hey, I didn't see you there. Oh, I was just showing my appreciation for my patron, you know? Don't ever take my sunshine away. Ever. Alright, anyways, let's get back to binary. Basically, before we start talking about binary, first I want to explain decimal. So, what is decimal? Decimal is the numbering system we normally use. There's 10 numbers, which is what deci means, D-E-C-I. So we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That goes through all 10 of them. So, we have a total of 10 numbers, which goes up to 9 because we're including 0. So 0 is 1, 1's number 2. Yeah, you get it. Basically, when we want to go to 11, we scoot that 1 over a place to the tens place. It might be this way for you guys. I don't know. Yeah, it'd be this way for you guys. Yeah, so this way. We scoot that number over to the tens place. We could add more numbers in theory if we wanted. So instead of having like a 9, we could have like a new number which would represent 10, and then a new number that represented 11. But that means we have to learn all those signs and also what they're called for every single number, which is in theory not practical. So what we do is we repeat the same 10 numbers that we have, 0 through 9. So every time we move up a place, we add a multiple of 10 to that number. Sorry, my hair's bugging me. Alright, so the way that works is we start with 1, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we want to add to 10, we move that 1 to the tens place, and now we have 10, 11, 12, 13, 14. You get it, because you guys probably understand decimal, and if you don't, then this video is probably not where you want to start. Right. So every time we move up a place value, we multiply it by 10. So in the hundreds place value, then the thousands place value, then the 10,000s place value. And shortly here, I am going to try and show you this on the desktop doing some arithmetic, you know. But for now, I'm just kind of explaining things. But for binary, we only have 2 numbers, 0 and 1, which represent off and on. So that way, when we go up a place value, it's actually multiplying by 2. So in decimal, back to decimal, it goes the ones place, tens place, hundreds place, thousands, 10,000th, 100,000th, millionth, 10 millionth, 100 millionth. In binary, it goes ones place, twos place, fours place, eighths place, 16th place, 32nd place, 64th place, and so forth. And when you take that binary number, you can multiply the place value, so like the eighths place, multiply by 1 since that's the number that's there, and then add that to the rest of the numbers and you get your final number. It's really not that complicated. I'm going to show you that on the desktop here in just a sec. When we're talking about possibilities of what we can represent with binary, you guys basically know it's infinite. We can make videos, pictures, audio, graphics, and so forth. Well, the way that works is the total possibilities that we can create with binary. But you may be wondering, how does that actually work? Because there's only 2 real options, on or off, so either a 1 or a 0. Well, we actually combine groups of those numbers to give us a representation of what it might be. Oh, my nose itches. So, think of it, if we have one individual place value, the ones place, we have 0, meaning off, or we could make that represent something else. So for a pixel on a picture, 0 could be black, or 0 could be white. Doesn't really matter. Now, 1 can represent the other one. So let's say 0 is black and 1 is white. And you could, in theory, make a picture out of that. So the first pixel is a 0, the second pixel is a 1, the second pixel is 1, the third pixel is a 1, the fourth pixel is a 1, fifth pixel is a 0, but that doesn't really give us a lot of possibilities. You see what I mean? So what if instead we use the combination of two binary numbers? So now we have 0, 0 is black, 0, 1 is light gray, 0, 2, or 1, 0 is blue, and then 1, 1 is white. So now we have a little bit of blue and anywhere from white to black. So that would give us more possibilities. That gives us a total of 4 possibilities. The combination of 0 and 0, 0 and 1, 1 and 0, and then 1 and 1. So that increases the size of the binary word, is what it's called. It's called a word. The length of basically how many bits are in that word. Bits is just a single, either a 1 or a 0. It's each place value, essentially. So with that example, we had a 2-bit word length, is how you would say that. Now, what if you wanted more possibilities? Well, you could say 0, 0, 0 represents black, 0, 0, 1 represents light gray, 0, 1, 0 represents blue, 0, 1, 1 represents white, 1, 0, 0 represents red, 1, 0, 1 represents green, I lost track where it was at. Anyways, you guys get the point. You can add more bits to give us more possibilities, and that is the idea of bit length or word length when we're talking about binary. So if you need more possibilities, you increase the word length. The word length is how many bits are in each individual word. So now rather than going 1 or 0, black or white, it's going 1, 0, 1, 1, okay, that's purple. And then it goes 1, 0, 2, or 1, 0, 1, 0, that's blue. And then 1, 1, 0, 1, that's green. And you can do that to create more complex things. So in that example, I was using a 4-bit word length. So that's going to increase our possible range of values. Now you'll most commonly see things like 32-bit and 64-bit. When we're talking about things such as audio, for example, when we're talking about 32-bit audio, or 16-bit audio even, that's how many possible different samples of audio we could have. Because think about if we only had 1 bit, we could either have audio or not audio. But you can't make a song with just audio or not audio. You need different frequencies and so forth. So, with that you can make it, a 2-bit word length. Now you can have different frequencies available. So if it's 16-bit word length, you have like 65,000 some options of each individual, basically you can think of it either as a frame or a sample of the audio. So with a CD, it'll do that 44,100 times per second with a total options of sounds of being 65,000. So every single second you're getting 44,100 different samples of audio played really, really, really fast. And each individual sample has a range of about 65,000 different options. And when you play all this really, really fast, you get what sounds to us like audio, even though in reality it's just binary at the fundamental level. Now when you're talking about hardware, operating systems or anything, when we're talking about like that kind of stuff, the 32-bit versus the 64-bit usually is talking about the bus. So basically, think of like a real bus, like a bus that can hold like 32 people can travel pretty good, but a 64-person bus is going to be able to travel the same speed, but it'll be able to send more people along, or bits basically. So that's what that's referring to. So when we're talking about samples or options when we're talking about pictures or video. That's the options. So if we're talking about bits or the bit depth for video, that's how many different options we have for each individual pixel, for example. If we have 8-bit, that's pretty low because that's like 250 or so options. And it's really hard to represent a picture like this beautifully, even though I'm so handsome, with only that many options. You need more possible options. So if you increase that to 16-bit, it gets better, 32-bit gets better, so forth. So if you go back to like the old gaming times and you're playing your Game Boy or whatever, and you have that 8-bit audio, you know, that sound you hear, well, there's only so many options because you can't represent very many options with 8-bit. So that's why you hear the same similar sound. It doesn't sound as good. I mean, to some people. I mean, I know a lot of you guys like that kind of music, but yeah. So that's understanding the options with binary, how it kind of converts to actual stuff we understand, like music, videos, and pictures. But how is it stored? Like on a hard drive, for example, we're going to talk about a magnetic hard drive. If you're talking like solid state, I don't even know. I mean, that's beyond me. But anyways, basically the way the hard drive works is it has disks that spin really fast, 5,000 times-ish a second. I mean minute, not a second. I'd be like, whew. But anyways, yeah, so that's called the RPM, how many times it rotates per minute. And then it has this other little, I don't even know what it's called, it's like a little dial that goes across the disk, and it magnetizes or reads the magnetization of the disk. So the disk is magnetic, has a magnetic coating, and the way that works is if it feels a change in the magnetic orientation, whether like positive or negative, I guess, then it'll put it either as a 1 or a 0. Put simply, you can go in depth on that if you really want. So the way that works is every single bit takes up a certain spot on the hard drive, and the hard drive can store tons and tons and tons and tons and tons of bits. In theory, okay? Now, when it comes to storing files, we have a file size measured in bits, or kilobytes, or bytes, or megabytes, or gigabytes. And that's what I'm going to explain now. Well, if you're talking about bits, a bit is this one individual binary number, either a 1 or a 0. When you have 8 of those, it's known as a byte. So if you have a 1 byte file, it's actually 8 bits. So you can store that on a hard drive with only 8 different bit lengths, or like magnetic changes, I guess, whatever. I don't know too much about hard drives, so don't take me to heart like, oh, that's not actually not correct, because I don't know that much. But when it comes to binary, a byte is 8 bits. So what about like a kilobyte? Well, a kilobyte is 1,024 bytes. And then what do we have after that? We have a megabyte, which is 1,024 kilobytes. And then we have a gigabyte, which is 1,024 megabytes. And then we have a terabyte, which is 1,024 gigabytes. And then I think we have exabyte or something. Yeah, we have a petabyte. And then a petabyte is 1,024 terabytes. And then an exabyte is 1,024 petabytes. So you can see it's like a tiered system. So that can get pretty complicated, but it makes it easier for us, because if we were counting bits and our file size was like, oh, 6,458,300,722,248 bits, well, that'd just be like absolutely astronomically impossible to understand when it comes to file storage. So they use the prefixes of mega, giga, tera, peta, exa, so forth. So when you're storing something like, let's say, audio in 16-bit, that means we have a total of 16 bits, or you can think of it as 2 bytes, because a byte is 8 bits. So 8 times 2 would be 16. So if you have 2 groups of 8, 1 byte and then another byte, you have 2 bytes, right? So a 16-bit audio sample, one of them would be either 16 bits or 2 bytes. However you want to think about it, it's the same exact thing, right? If you have 32-bit, on the other hand, it's going to be 4. So the higher bit rate of the audio, the more storage it's going to take to store it. Because even if you're only using a certain sound that, like, the last 3 bits are 101, it's stored as 000000000, however many zeros, 101. And then that whole group of bits is stored together to represent a single sound. So the higher the bit rate, the more preceding zeros, or I think it's preceding, the zeros that come first when you're looking, the more those you're going to have. So if it's 8-bit, it's going to be 000000101. If it's 16-bit, it's going to be 000000000000101, I think. And that whole group is going to be stored as a group. So the higher the bits, or the more the bit length or the bit word length, then the more storage it's going to take. Also, for audio, while we're on it, the higher the sampling rate, the more storage it's going to take, because you're going to get more samples per second, which means you're going to have to store more samples. So it can get pretty quickly. It can get pretty large pretty quickly if you increase the bit rate and the sampling rate. The same concept applies to pictures. It's just a little slightly different. I just think audio is the easiest to understand. So, yeah, you buy a hard drive such as, I don't know, a terabyte hard drive. That's going to store 1,024 gigabytes. When you might be wondering, why is it 1,024? Well, binary when it comes to electronics is in base 2, which means it multiplies 2 every single place value. So you got, I can go through these again, hopefully I don't mess up. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So it can't represent 1,000. That's just not going. That's why it's in 1024, because we're in base 2 system. 1,000's not going to be easily represented if we're talking about place values. It just makes sense to go with the place values. So what I mean by, I guess it go this way. The place values would be like 1 would be 1, but then 10 would be 2, and then 100 would be 4, right? So that's basically all about the size of the data and the bit word size. Yeah. So one other thing I want to talk about is internet speed, because I think this is a really cool topic. So when you buy internet, they'll say something like, I don't know, 8 megabits per second down, 1 megabit up or something. I don't know, mine's much lower. It's like 1 megabit down and a small fraction of that up. But I can't complain, it's functional, so that's good. But anyways, that's, if you're talking about storage size, that's kind of deceptive, because everything that we store on computers is stored in bytes. We don't really think too much in bits, so it'll be like, this file is 1 byte, or this file is 1 megabyte. But when we're talking bits, it's a smaller than that fraction. So if you think you're going to get 1 megabyte, let's say we're talking in 1 megabit per second download speed, and you think you're going to be getting 1 megabyte per download per second for the download speed, that's actually inaccurate. It's actually going to take 8 times as long to download something, since there's 1 byte. There's 1 bit in a single byte. So just keep that in mind when we're talking about, like, if we had 1 byte down, it'd be what you're thinking, but it's actually in bits. So it's a fraction of what storage usually is. So keep that in mind. If you had 8 bits down, that'd be the same thing as 1 byte down. But internet is almost always told in bits per second, just because that's how they measure it. So just keep that in mind. Yeah, moving on. Alright, so now we shall begin the part where we draw stuff, you know. I'm also using my new microphone here, so you can tell me if that sounds better than my other one. So hopefully it does. Otherwise I wasted a ton of money. Alright, so let's begin with just going through some binary numbers. So we might see an 8-bit binary number like this. And I know my handwriting is just so bad, but I mean, I can't be one of those guys who draw like perfectly while making a video. It's just not possible. I don't know how people do that. All right, so this whole number right here, this is a word. And the word type we are using is 8-bit. That's because we have 1, 2, 3, 4, 5, 6, 7, 8 bits in one individual word. Then we could attach another one right beside it. Yep, there we have 8. So this is going to be a second word. Alright, so this is kind of how it works. Now, how do we actually figure out mathematically what these numbers are? Well, every single place value has, you know, a place value. So the first one, let's say we have a 1 here. This is the 1's value, and then we have the 2's value, the 3, I almost said 3's value, the 4's value, the 8's value, the 16's value, the 32nd's value. Let's just go to 8. All right, 64, and then 128. So how do we go about, like, let's say this right here was our word. How do we go about calculating what this value is? Well, there's a couple solutions. You could, one, go to a calculator online, just put that in there, and boom, you're done. Or you can you could actually use the calculator that comes with your computer, I think. Let's try this out. So you can go to programmer, and you can put 1, 2, 3, 4, 5, 6, 7, 8, and that's gonna be in oh, darn it. Okay, you gotta put that in first, so clear it. Then put it in binary and go 1, 2, 3, 4, 5, 6, 7, 8. And then you can change that to decimal. So we know this is the same as the decimal 255. This is how we would write 255 in binary. But what if we don't have a calculator at hand and we need to figure out how to do that? I know. When would that actually ever happen? But whatever. Let's do it just for learning's sake. Basically, we take the place value, and if there's a value there, we count it. If not, we ignore it. So if we look up here at this word, where this 0 is, we wouldn't count that place value since there isn't anything there. It's either a 1 or a 0. Yes, we count it, or no, we don't. Here you can see that every single value, every single place value has a bit that is a 1. Therefore, we need to count every single one. So let's do that. So the first one here, I'm going to use red just to make it pretty, you know. All right, so the first one here, we have the 1's place, we have the 2's place, 4's place, 8's place, 16's place, 32's place, 64's place, and 128. Now, how do we figure out a number from this? Well, basically, we're going to take all of these and we're going to add them together. So if I get my calculator back out, I'm going to use the keyboard for this, actually. Let me move it aside a bit so we can see. Let's just go back to the normal standard calculator. We got 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. We get 255. All right, let's try a different one. So let's just scroll down here a bit. Let's say we have the number and this is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So how do we do this? Well, basically we take the place values that we need, which, let me underline them here, would be this one, these two, and this one. Don't even worry about the zeros. They have no practical purpose in this, but they do still keep the place value, so that's important. But you don't need to calculate them. That's what I mean by that. So let's do this. This is the what is this? This is the ones place. It's the 2, 4, 8, and then we're on the 16s place, and then we're on the 32s place. I should say. It's not a fraction, so it wouldn't be 32nd. And then we have the 64 and the 128. So if you're going to get confused by crossing those out because you're going to skip them and accidentally say this is like the 64 place, then you might want to just still do that. Just do it in a different color or something so it's easy to see. This is the 2's place. This is the 4's place. This is the 8's place. And that is the 64's place. And then you can basically ignore those numbers. And basically you want to take these green ones here and add them together. So we get 1 plus 16 plus 32 plus 128. Let me get my calculator back out. We got we get 177. Just let me double check that that's correct by going to the programmer calculator, putting it in binary, and then typing in our number here. We got 10110001. And then we got to put that into decimal. Here I'm like clicking equals. It's like, oh, it's not doing anything. We get 177. So it works. All right, cool. So I'm not going to get super in depth in how to do like arithmetic, like adding and subtracting, because I have other videos that go over that in depth, and I don't really think that it's that important right now. But I do want to just kind of illustrate maybe an addition problem and a multiplication problem, just so you kind of get the idea. But we're not going to do tons of practice with this, so don't worry. Let's just use 4-bit words, so that way we have 4 place values. Right? This is 0, so that's just kind of like our, just to show how many place values we have. And let's add 0, 1, 0, 1, and 1, 0, 1, 0. And then we're just going to add these. So how do we add? Well, it's pretty simple. Whenever you add them this way, just like we do normal math, 1 plus 0 is 1. 0 plus 1, 1. 1 plus 0 is 1. 0 plus 1, 1. And this is our final answer. And you can figure out what that is if you want in decimal, or you can just turn it in like that. What if it gets more complicated though, where we actually have to carry things over? Like let's do this. In this example, we have a different situation because the ones here, we can't just drop a 1 like this, because 1 plus 1 doesn't equal 1, it equals 2. Whoops, I didn't mean to zoom out, I'm zoom in. So, what do? First, figure out how do you write 2 in binary. Well, we know that if we're looking at the place values, this is the 1's place, and this is the 2's place in decimal, I guess. So the way we would want to put a value here in the 2's place to represent 2. So to represent 2, we would have that right there. Now, when we're working with this problem, we don't actually need these zeros here, the trailing zeros or the leading zeros. I don't know, I get those two confused. The zeros before the actual number. but come first when you're reading it. I don't know, it's confusing. But anyways, this is how you write 2 in binary. You don't actually have to worry about the word length because we're just using it within our question or problem right here. So now we're going to take this and we are going to carry the 1 and drop the 0. And then we just do the same thing. 1 plus 1 plus 0, that equals 2. So we did the same thing. Carry the 1, drop the 0. 1 plus 1 plus 1, that gets a little more complicated because now we have 3. So how do you represent 3? Like this. So we got a 1 in the 1's place and a 1 in the 2's place. So we get 3. So you just carry the 1 and drop the 1 because that's how you write that. Yeah, it looks like a face. Okay, now 1 plus 1 plus 0, that equals 2. So you just carry the 1, drop the 0, and then finally we're going to drop the 1, and we get this final answer. And you can check me if you want. I don't really care. Like, I don't feel like checking right now. So let's just do a little conclusion for that. If you have it to where, let me scroll back up for a sec. If you have it to where you're adding 1 and 0, well, let's go with 0 plus 0. It's going to be, 0. Then if you have 0 plus 1, it's going to be 1. And we're just going to do this just so you kind of understand how to carry things. So you got 1 plus 0, or basically the same thing as the other one, so I don't really think that's necessary. Let's just go 1 plus 1. That's going to give us 1, 0. And then if you have 1 plus 1 plus 1, it's going to be 1, 1. And then if you have 1 plus 1 plus 1, oh man. Plus 1, plus 1, plus 1. That's going to give you 4, which is going to be 1, 0, 0, and so forth. So if that was a situation where we had to add 4 1s together, we would carry up 2 positions. So if it was like this, we would carry up 2 positions. So above this one, we would put a 1. And then we'd come down here, we would drop a 0 below both of these. That way, so you can take this number and basically put it into this situation where we have 1, 0, 0, and then do the rest of the problem. So 0, 1, that's, yeah, you get it from there. So that's how you do that. And yeah, multiplication, it's pretty similar. It's going to take, let's do a simple one, 1, 0, 1. And 1, 0, 1. Okay, so for this, you're going to take this number and multiply it by this number down here. Now, here's a little trick though, because since you have 1 times 1, 0, 1, you basically just copy it down because 1 times anything is itself. So let me get a different color to put the answer here. You can get 1, 0, 1, and then we're done with that one. Now we have to go to the next one, and for this we're going to move up a place value. That's just what we do in multiplication. And we're going to do the same exact thing. 0 times 1, 0, 1. Well, that actually equals 0, so we don't have to worry about that. Done with that one. Now we just have 1. We got to move up 2 place values because we're in multiplication. 1, 0, 1. Great. Now we do basically addition with this new problem here. 1 plus 0 is 1. 0 plus 0 plus 0 is 0. 1 plus 0 plus 1 is 1, 0. 1 plus 0 plus 0 is 1, and then 1. So this is our final answer, and you can convert that to decimal if you really wish. So just by doing a couple practice problems, like look at all this mess we have, that just kind of helps you understand how the actual binary works. Yeah, it's pretty sweet, actually. Okay, so now that we're done with that, we can actually draw some fun things like a face. Looks kind of creepy if you ask me. I don't know what that is. I kind of screwed up on that. Yay, he's so happy. And he lives in this house. It looks like that one, that Pokemon that's like, I don't know, he's like a floating ball. And he has like a big scary a face on him. He's like, and he has like stuff around him. I don't know what he's called. It's from like the old generation Pokemon. Alright, well, that's it for that. Alright, so that's basically all I really want to say about binary today. I mean, actually, I think I'll go over one more thing really quick now that I'm here. Alright. When you get into more complex binary, there's things such as 2's complement, which you guys may have never heard of that. I'm not going to cover that in this video, simply because it's really complicated. And to be honest, I'd probably have to relearn half of it. But I did make a video about that, and I encourage you to check that out. That gets for more complicated math problems and how things are actually stored in a database. It has to do with signed and unsigned binary numbers. And what that is, basically, if a number is signed at the beginning of the number, so it'd be on your guys' left, this side of the number, so basically 10101, that first digit, I guess it's not a digit, the first bit is a way to tell if the number is able to be negative or positive. So if it's a signed number, it has the capability of being considered a negative number. If it's unsigned, it's always positive. There's good and bad sides to both of that. Since it actually takes up one of the bits, it decreases the amount of possible numbers you can use, you see? Because if you have an 8-bit word length and the first bit on the left is being used just to say if it's positive or negative, now you only have 7. And that can be good or bad. If you need negatives, yeah, that's good. But if you don't need negatives, I recommend not using signed bits or signed binary numbers or whatever. Now, it gets even more complicated than that. So basically, from here, I recommend you go check out my other binary videos. I have Introduction to Binary, Adding and Subtracting Binary, Multiplication in Binary, and then 2's complement. Don't know if I have any other more than that. Now, on top of that, there's also something known as hexadecimal and octal. Those are also numbering systems, meaning that they work the same way as decimal and binary, except the amount of numbers they have is different. Hexadecimal has 16, and octal has 8. That number that keeps changing, either 10, 2, 16, or 8, is known as the crap, I think it's the radix. Let me just double check that. But basically, the radix is the base of the number, meaning how many number possibilities they have. So for hexadecimal, you have 16. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, and then it starts using the alphabet instead of numbers. So that's kind of confusing, and that's something you need to get used to when you're working with that. Same for octal, except instead of having more than base 10, it has less, so you only go up to 7. Because you got 0, 1, 2, 3, 4, 5, 6, 7. So I also have videos over hexadecimal and octal. Check those out. Works the same way, so if you get binary, you should be able to pick up on those pretty easily. Those are also important to know when it comes to computer science and just electronics in general. So check those out, guys. And other than that, I just encourage you to subscribe. You know, I think I'm going to go answer some questions right now on YouTube. So let's do that. So I've been getting a bunch of comments and questions and stuff, and basically I'm overwhelmed with just like possibilities. I mean, like time-wise, it's basically almost impossible for me to reply to them all with good detailed answers. So I want to start doing them in videos because I think that'd be awesome. I could start making more videos about cool stuff. Answer people's questions is a win-win because I get more videos, you guys get your answers, it's more interactive, it's awesome. So, first things first. Since this doesn't necessarily have to be about binaries, this can be anything. Let me go to my comment section. So you go Creator Studio, and then you go to Community, and then you go to Comments. Good. Alright, so, first, hi, Apache won't start, and then when I input localhost etc to browser, Chrome, nothing happens. Well, they actually fixed this problem. He said solved. Port 80 turned on from Skype. What does that mean? Well, basically for a local server, you need to use a port to access that server. It keeps it open for your access to do your stuff on. By default, Apache uses port 80 and a couple other ports like 443, for example. If you have a program that's already running on that port, it's going to cause a problem. That's because you can't have two programs using the same port. So for example, if you guys haven't heard of IIS, that is basically another web server aside from Apache that also uses port 80. So if you already have that installed and then you try to install XAMPP or XAMPP, however it's pronounced, or LAMP or whatever, it's going to cause problems. That's because that port is already being used. And then when you go to port 80, it's going to cause, it'll probably go back to the original, the IIS port that was being used, so the IIS homepage will come up rather than your Apache homepage. In his case, he was having port 80 being used by Skype, and by default Skype does use those ports, so if you want to fix that, you have to go into your Skype advanced settings and you can disable using port 80. It's really simple. I could make a video on that. I've actually done that because I was in a situation where I was using Skype, but I was also web developing on local server, so I couldn't do that both at the same time, so I had to go disable that in Skype. You are so awkward. LOL. Thanks. That makes no sense. Sorry. Thanks. Alright. Those aren't questions, but I think I just want to read some comments too, because I like these. Alright. Let's see. Caleb, I was researching for some one-to-one tables I'm making, but someone mentioned that it harms the relational nature of the database. Is that accurate at all? So, for this situation, a one-to-one relationship, if you don't know about databases, this is probably going to go way over your head. But basically, an entity is a connection, has a connection with one other entity and no other entities in that relationship, basically. So you think of a person's name and a person's body. You wouldn't really store the person's body in a database unless you had a picture of them or something. But that name, that individual person's name is associated with that person's body, and that body is associated with that person's name. It's an awful example. But anyways, for that, he's wondering if it's bad to store one-to-one relationships over multiple tables. And the answer is no, it's not a bad thing to do. But it's not always necessary. Because if you have a one-to-one relationship, 90% to 95% of the time, you can just store that as a column within the other table. Because there's no need to make another table for people's names and then use that name, reference it with a foreign key. Because that's going to make more tables and more foreign key connections, which requires more foreign key constraints, which slows things down, and it just causes more problems. So in that situation of storing people's names, the chances of someone having the same name as me, Caleb Curry, or even with the same middle name, is high, but it's not that high. There might be a couple people that use the same name on whatever this application is that you're building. So I don't think it's necessary to design it as a one-to-many relationship. So I'd store that as a column within the original table, the user table or the person table or student table or whatever. That being said, if you need to store information about that one-to-one relationship, you'd have to put that in another table. So that would be called a transitive dependency, meaning that we have data relying on data that relies on the primary key. But that's a whole nother ballgame. So it's not necessarily bad to store one-to-one relationships over multiple tables, but only do it if it's necessary. And for that, you need to understand database normalization. So study up on that. Okay. Yep, so I don't know what else to... Alright, MySQL, NoDB engine, and foreign key constraint slows down queries. As long as you don't perform, for example, banking operations, I would avoid them. Alright. I kind of disagree. Yeah, they do slow down queries, but it protects your database integrity. So, if you don't want to use those constraints, you need to denormalize your database some so it's not spread out over so many tables. Because if you have it to where it's set up over multiple tables and something updates over here and something doesn't update over here because you didn't have that foreign key constraint, well then your database is totally worthless. So yeah, I disagree. I see your point, it does slow down things, and if you are in the situation where you don't need to use foreign key constraints at all, or anything like that, you might want to look into NoSQL, not only SQL, which is a form of database. There's tons of them, so check that out. That's for tons of data. That's stuff like Facebook and Amazon and Google uses, so... Dude, too cool. Sweet job. You got my shirt on. Congrats on having a brain. Yeah. What collation could I use for English and Japanese in the same column? I think you can use UTF-8, basically, or the, just the standard, what is it, Latin or something, I don't even know. That'll probably get most of the most common languages. Why did you have to call the police? I actually don't know what that guy's talking about, but I'm guessing it's because Claire. The end. What will happen if we delete any value from parents table to its child table? Alright, so basically this person is asking in databases, what happens if you delete the parent when you have a child? And that depends on your foreign key constraints. So basically when you have a parent and a child, there's a connection to that parent through a foreign key. That child references the parent. If you delete that parent, you can either cause it to throw an error or to also delete the child. You could probably do other stuff in different databases, so it really just depends, but you would want to look into foreign key constraints for that. Thank you! You made two's complement more understandable. So two's complement is the thing I was talking about earlier when it comes to more complex storage of binary. Definitely need to check that out if you're going into binary stuff. That's really important. And this guy says that being completely new to this, I was confused as to why you carried the 1 when you did. Maybe that was in another video. to answer that, yes, it was. There's introduction to binary and the other binary videos that I told you guys about earlier. So you might want to check those out before you check out Two's Complement. But if you feel comfortable, go ahead and do it. Yeah, I think that's all for now. I don't know what else to talk about. Alright, so yeah guys, thank you for watching, and a couple things before you go. If you liked this style of video, it's a lot more laid back, to be honest. Please tell me, because I'm just like totally confused with what to do with, I'm gonna do the tutorials all the time, the lessons, but I don't know if I should make them longer, shorter, more in-depth, less in-depth, harder. I want to make the best videos, so I like doing this. Like, what do you guys think about me doing more laid-back videos every once in a while, just where I talk for, just kind of like a talk show, something you just listen to. I mean, I like the idea, except I don't know how practical it is, because I don't know what I talk about for half the time, because my skill set's kind of specific. I mean, I've already talked about everything I know, so... You know what I mean? So, I don't know. And let me know about that. Be sure to subscribe for future content. That'd be like super helpful. Extremely helpful. Also, anybody interested in sponsorship, sponsoring me, send me an email. I got my email on my YouTube channel, and we can talk about that. It'd be cool. Alright, yeah. So thank you for watching. Be sure to subscribe, and I will see you in the next video. Peace out. Peace. Peace out. Like my new shirt.